lectures on the Boltzmann equation and Hilbert's problem, and then Thursday take a break, and then next Tuesday and next Thursday I'll continue the lectures I started the last visit here, which is on the conservation laws of differential geometry, and I'll try to go slowly. I thought, because I didn't do it last time, I'll write down the conservation laws and show the amazing thing is that the conservation laws of differential geometry are exactly the same as what I do in this lecture for gas dynamics. So two problems, completely unrelated, same equations. That means we can use the techniques of one for the other. Depends. If you're a geometer, you can then do things in fluids, and if you're a fluids person, you can do things in geometry, and you don't have to learn anything new, just realize that the equations are the same.
So Tuesday, Thursday, next week, same time? Same
time, same place. Yeah. Okay, so today I don't know how long it'll take, but I have this lecture that I had prepared for when I was in Oxford in September, and I'll give the same lecture at Post-Tech on Friday, but it's very convenient to have it here, and that way it summarizes everything I've done so far and then shows us the ideas, so I don't have to spend the time filling the blackboard with lots of equations. As I said, the worst thing of this subject, both Boltzmann and geometry, is too many equations. And with subject with too many equations, you can miss the important stuff from the unimportant stuff. So the nice thing of thinking about both subjects is let's think about it and let's realize what's important and what's technical and not so important. And if we do that, then we don't get lost in the technical stuff and we see the big picture. And that's my claim, of course, is that in this Hilbert 6 problem, I claim the people in there spending all their time on the technical stuff miss the big picture. Okay, so that's the title, not very exciting. So let's start with the story. And what's new here is I'll introduce for the first time this Gorban and Karlin papers that play such a key role. Okay, Gorban is a friend of mine, so he used to be in Russia but moved to England and now is at the University of Leicester. And Karlin was his PhD student in Russia, and he now moved to the chemical engineering department of ETH in Zurich. Okay, so here's the story of the Hilbert problem, so I'll just review that while I'm here. So Hilbert proposed in many things, but in the axiomatization of mechanics, one part of that is, can you go from the Boltzmann equation to the compressible equations of gas dynamics, the Euler equations, as this small parameter measuring mean free path goes to 0, which is the Knudsen number. Okay, and as I said, as of this moment, success in this problem has been limited to the cases where the limit equation, the Euler, has smooth solutions. That is before shock formation. But after shock formation, no results. So we can think about it logically, philosophically. Are there no results because we're not good enough mathematicians, which may be true. We haven't invented the mathematics we need to do the subject, or it's just not true. And my feeling is it's the second one. We have enough mathematics, it's just not true. Okay, and I said one of the goals of the research was, can you explain if it's just not true, if it's not simply, don't give me complications. Can you explain it in a simple way that everybody who understands couple of years of undergraduate math can follow. Okay, so here let's review, which I did in previous two talks. So there's our friend the Boltzmann equation. Okay, and as I mentioned last time, Hilbert himself tried to solve the equation by a matched asymptotic expansion, but the better version is to do a matched asymptotic expansion in the macroscopic variables, which I called M. So we look for an expansion of the solution to the Boltzmann equation in a formal asymptotic expansion where f depends on xt through the m. And what's m? M means the density, the macroscopic variables that we would use this in continuum mechanics. That is the density, say, of the air in the room, the velocity of the air in the room, okay, and the temperature of the air in the room, and its space derivatives. Okay, so that was the idea of Chapman-Enskog. It changed the whole view of the Boltzmann equation. Okay, so, and if we do this expansion, I remind you that if we truncate at 0th order, we get the Euler equations. If we truncate at order epsilon, we get the Navier-Stokes Fourier theory. And if we truncate at the epsilon squared, then it's called Burnett equations, and then epsilon cubed, so-called super Burnett equations. I remind you here it's in blue. Okay? So the success of the Chapman-Enskog expansion to give us Navier-Stokes Fourier, sometimes abbreviated as NSF, which did not pay for this research, okay, has motivated many to view the Navier-Stokes Fourier theory as fundamental way to think about how to find what's going on in the shock wave. That is, you write down the Navier-Stokes Fourier theory. Okay, you have some small parameter epsilon on the right-hand side, and you say, okay, let's pass to the limit as epsilon goes to 0. Okay, but that justification, in my opinion, is nonsense. Okay, nothing more than nonsense. Okay, so let's, here, now this is new, I didn't do this before. So let's think that you wanted, I have chalk here? Let's do it on the board. It's so simple and yet so crucial. Let's say, everybody can see this? All right, big. Okay, so there, this isn't Euler, but same idea. Okay, scalar conservation law. Everybody knows about the scalar conservation law. Solutions exist for a little while with smooth data, and then depending on the first derivative of the data, okay, we may have blow up, and if we have blow up, that means we have a shock forms. Okay, how can we study whether it's an admissible shock or a non-admissible shock? That is, a shock which is the characteristics are running in, or a shock which the characteristics are running out. The good one is when the shock's characteristics are running into the shock. The bad one is when the shock characteristics are running out from the shock. Okay, what's one way? Let me get the thing. If you haven't thought about this, where's the thing? Okay. Okay. Let's just do it together, because it's crucial to the whole story. So what mathematicians have done over the years, the idea goes back to von Neumann, Gelfand, and von Neumann in fact had a motivation. It's not crazy, because if you try to write down a finite difference approximation to this, okay, and you use a good finite difference approximation, say the Lax-Friedrichs, I won't go into it, you're imitating this term, so it makes sense that not only you're putting it as a PDE, but you're also capturing the essence of the numerical analysis. So then, how do mathematicians decide whether this is a good shock or a bad shock? And what they do is they look for a traveling wave solution. So let's say the good shock, okay, there's some shock wave on the left, it's u minus, on the right it's u plus. This is t, this is x. Okay, so you'd see a shock wave, okay, and we'd see the solution on the left is u minus, on the right is u plus. How can we decide whether it's a good shock wave or a bad shock wave? And what we would do is, historically, okay, we would look for a solution x minus ct over epsilon. Okay, plug it into the equation. Okay, and we would get, by the chain rule, we will get over here, we get a minus c over epsilon u prime. Here we'll get a u prime over epsilon, and here we'll get u double prime over epsilon, because it's epsilon upstairs and epsilon squared downstairs. We do the obvious cancellation, and we get an ODE. Okay. Of course, we can integrate up once on the ODE, and we look to see whether the solution to the ODE will connect at minus infinity, say u minus, and at plus infinity u plus, which is a connecting orbit problem, trying to go between the two equilibrium points. If we succeed, which is the case of the good shock wave, okay, then we say that's an admissible shock, and it's satisfied a viscosity admissibility criteria, and we're happy. Furthermore, okay, we can even ask the deeper question. Okay. Can we pass to the limit as epsilon goes to 0 to recover the solution of this equation? And the answer is, indeed we can. Okay, that was first shown by Hopf-Cole. You make a change of variables, you can pass to the limit and solve the equation explicitly. Okay, so you can pass to the limit. So putting the viscous term there works. That's the good news. Okay, and passing to the limit. But now let's continue. So that's the historic justification, which in some sense, mentioning the Euler equations, is what you would do with the Euler equations if you put in the Navier-Stokes Fourier theory. Everybody with me? This is the most important thing I have to say, and it's so simple. Okay, so there's the traveling wave solutions. Okay. On the other hand, let's think about it. I wrote it there. What happened when we look for the traveling waves? It's trivial. It's so trivial, nobody thinks about it. Well, some people think about it, but not as many as you'd think. Okay. When you're looking at the ODE, there are no small terms. All terms are the same size because we've scaled out the epsilon. All terms are the same size. There are no concept of small. That is, within, what are we really doing? We're looking in the shock layer, small layer around the shock wave, and we've said, okay, this is going to be the information we'll put in. No small terms. So the highest derivative term here is just the second derivative. Okay. No concept of small once we go into the shock layer. I wrote it here in red because it's so fundamental. There is no concept of small derivatives at the ODE level. All terms are a priori the same magnitude. Okay, I say that there again. The epsilon has been scaled out. Hence, any subject of non-smooth hydrodynamics based on a truncation of the Navier-Stokes equation, stopping at order epsilon, is nonsense. My own opinion. But it's a rather, nonsense is being a little harsh, but that's my opinion. Okay, it's an illegitimate use of the Chapman-Enskog. If you like Navier-Stokes Fourier, good for you. Use it. But don't say it comes from the Boltzmann equation. Okay. That's not true, because remember, the Boltzmann equation, to develop the theory, as I just said, if we follow Chapman-Enskog, there was order 1, order epsilon squared, and if we plugged in, all terms are the same size. You can't just stop at order epsilon. Now, I view this as something coming from a way of thinking about history, okay? And here it is in Latin. If you like Latin, good. If you don't like Latin, it's okay too. Okay. So I doubt Latin is taught so much in the Korean schools. It's enough things. The students of high school are going from morning till night anyways. I don't think they have time for Latin. Okay. Latin, of course, in the U.S. system, when I was young, they still taught it. Now, finished. Okay. But Latin is a useful language in this historic scholarship, and the word is vacinium ex eventu. But assuming you don't know what the Latin, I give the English translation. It's one of my favorite phrases, and I give the reference to the book I get it from. So it's a pseudo-prophecy written after the event. What does it have to do? I'll say, what does it have to do with math? Okay, it means, okay, in my opinion, the engineers like Navier-Stokes Fourier. It works. Okay. You want to find if outside of a shock wave works? Fine. Okay. So they like Navier-Stokes Fourier. They want a justification for Navier-Stokes Fourier. So they say, oh, it comes from the Chapman-Enskog expansion. We just keep the first term and throw away, that is the epsilon term, and throw away the rest. But that's, as I said, a prophecy written after the event. Okay, okay. They don't start with Navier-Stokes Fourier, with Chapman-Enskog, and give a good reason to cut. No. They say, I like Navier-Stokes Fourier, hence I'll cut at order epsilon. So knowing what they want, they give an excuse. But that's not math. That's philosophy. In fact, this sort of philosophy. So it makes no sense. If all terms are the same size, how can you stop after the first term? Of course, outside the shock, when you have smooth solution, makes sense. But for non-smooth solutions, makes no sense at all. Everybody with me? This is, again, no math, no writing, just thinking. Nobody, all you have to do is think. Okay. So as I said, I say, if you want to study weak solutions and truncations of the Chapman-Enskog are illegitimate, then what can you do? There's only one choice. Don't truncate. Which means you have to add up the entire expansion. Okay. Seems impossible. How can you add up the entire expansion? First derivative, second derivative, third derivative, fourth derivative. Okay. Amazingly, at least in a special case, we can do it. And my homework assignment is to you is, I think it can be done in more cases than in these guys' papers. So I give references, but all you have to do is be clever, I think, and you should be able to do it, in fact, for the linear Boltzmann equation. No one's done it, but I think it's doable. Okay. Now, okay, so let's see what these guys did. And they're all in English, okay? Even the ones from when they were in Russia, and they were published in English translations. So I give all the references in the papers that are on the website, I hope. So let's continue. No? There. So now what did they do? Okay. So as I said, I wish I could do the Chapman-Enskog expansion for the full nonlinear Boltzmann equation. Oh, it's a big mess. Even the first two terms are a big mess. Okay, so think of the simplest thing we could do. And the simplest thing we could do, well, next simplest thing would be the linearized Boltzmann equation. Okay, that's already too complicated. So what's the simplest thing to do is, let's go through this moment story that I started with last week. And we do these moment equations. So we do, as I said, you write down the first moments. Okay, that gives you, would be something with Euler equations. Then you write down the next one, that gives you some more extended equations. So let's stop after, as I said, at this level, and then linearize. Linearize about what? We linearize about the rest state, which is velocity equals 0, of constant density. So this is not rho, but rho perturbation off a constant temperature density, and temperature, again, not temperature at absolute 0, linearized about some temperature non-zero. Okay. So write those down. So we take the Grad's 13 moments and we linearize. Okay. Just to make pressure enters it, so let's say it's density, velocity, temperature. This is sigma, the extra stress. It's the stress is pressure plus this leftover guy sigma. Now the only notational difference here is what I called plus sigma in the previous two lectures. Gorban and Karlin called minus sigma. So this is a sign change here, but that's irrelevant. Q, which is heat flux. And if it makes sense, let's see, what is pressure? Well, remember, pressure is roughly density times temperature. When you linearize rho times theta, you get rho plus theta, right? It's the product rule for differentiation. And you said rho equal to, around theta equal 1, rho equal to 1. So that's just been normalized to keep it simple. So the pressure is just rho times theta. So let's see. There are, if you count them all, 13 equations, which that's why it's called Grad's 13 moments. As I said, I wish I could do this Chapman-Enskog story for more moments, and somebody, if you want to, you can. But my thought again is, if you see the idea at the simplest, then you see how to do it further and what goes wrong with this Navier-Stokes Fourier business. Okay, so everybody with me? So let's review. We do the Grad 13 moments, because I can't do Boltzmann. I wish I could, but I can't. Okay, so I can't do Boltzmann, I do Grad 13 moments. This is without the, no epsilon here, okay? But it's not hard. If we just rescale, we get the Knudsen number. So I think that's, so let's rescale. So now we get the Knudsen number. Now I have the pointer, this one, which is the middle one, or this one? Yeah. Okay. Now, so there's the Knudsen number. Not only did I do 13 moments, let's go back. Can I go back one? Okay. I said, this one, I could do the Chapman-Enskog expansion, and it's in the book, the papers of Gorban and Karlin. But let's make things even simpler, okay, and do a simpler version, and that is if we set Q identically, so throw away this equation and set Q equal to 0. Okay. Then we can get just 3 equations, because the temperature equation in fact just becomes a combination of the other ones. Let's go back. And we get Grad's 10-moment theory in one space dimension. Okay, so it's even simpler. So what could be simpler than this? Okay, you have 3 equations, okay, P, U, and sigma, 3 unknowns, P, U, sigma, okay, okay, and now the epsilon is there. So if you're with me, okay, we've started with this big problem of Hilbert and Boltzmann and all this stuff going back to 1900, and I said, oh, let's reduce it to the simplest thing we can think of to see what's going on. And the simplest thing we can think of to see what's going on are those three PDEs. Linear. Okay, so now let's do the Chapman-Enskog expansion to see if we can learn. You'd think, I must admit, three linear PDEs. So there's many papers written on this case, linear, nonlinear. Okay? Okay, people will prove existence and smooth solutions and all that stuff. Lots of things. But the one thing they won't tell me is what can you learn from them? Okay. And that's the essence. You can learn a lot. Okay. So it's not so much writing down the equations as asking the good question. Okay. So what's the good question in my opinion? Of course it's personal. Okay. So I say, we'll follow Gorban and Karlin. They did this computation. You write down the Chapman-Enskog expansion for sigma, because I try to close the system, okay? Because if I then find sigma by the Chapman-Enskog expansion, then instead of having three equations, I'll get rid of sigma, and I'll just have two equations. And all the information will be in those two equations. So the idea is solve for sigma, not by doing the integration. I know I can do that. That's not the point. That just trades one thing for another. No, I want to solve for sigma using the Chapman-Enskog expansion. Okay, so let's do it. Okay, so we're making the expansion for sigma, where sigma is allowed to depend, each term in the series, because it's a Chapman-Enskog expansion, means it can only depend on the macroscopic guys, P and U, and their space derivatives. So let's do the first term. Okay, with the... Okay. Now that's so the first term is easy. Let's multiply. So the right-hand side becomes d dt sigma multiplying by epsilon equals, minus 4/3 epsilon d dx u. Right? So that's the third equation there, minus sigma. Right? But sigma, I said, is minus 4/3 d dx u. And we expand sigma, u. And according to Chapman-Enskog, we write it as epsilon sigma 0, epsilon squared sigma 1. Remember, the 0th order term is the p. So let's do that. So we do epsilon sigma 0, epsilon squared sigma 1, etc. Okay, so the first term is easy to pull off, right? So it means this order epsilon term has to balance that epsilon term, which as sigma 0, the first term looks like epsilon du dx. Okay? So first term with the 4/3, epsilon du dx. Okay, so we pulled out the first term. Well, if you think about it, okay, that says this thing will look like d dx of d dx of u with the 4/3. That's Navier-Stokes. It's the viscous term. So without going through all the complications of the general case, we see we've pulled out Navier-Stokes, and if we did with the temperature, Navier-Stokes Fourier. So at the first level, even for this simple grad version, we pull out Navier-Stokes Fourier. Okay. Now the next level gets a little complicated, and I'll sketch how it's done, and it's in the notes that I think I worked it out. So, but let's just do it. So you'd have d dt here. Then I have to plug in all this guys. But I know the first term already. So it's epsilon 4/3 u sub x, because I know sigma 0. And then I have epsilon squared sigma 1 plus dot 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 equals minus 4/3, right? It equals minus 4/3 dx du minus sigma 1 over epsilon, and over here is epsilon sigma 0 plus epsilon squared sigma 1, etc. So far, so good? Okay, well, these two guys cancel, because the epsilon goes into there, because that's what's rigged up. So now we see we have a formula for sigma 1. It says d dt of epsilon u xt, 4/3, right, plus epsilon squared d dt sigma 1, right, equals sigma 1. Did I do that right? Let's see. Epsilon, yeah, equals sigma 1, right? So at order, this is epsilon squared, so not relevant. So I can pick off sigma 1. It says sigma 1, oh, sorry, it's uxt, right? d dt uxt. Now here's the whole idea of the Chapman-Enskog. Okay, we have an xt derivative, but what's u sub t? Sorry. The leading order, can I do the, yeah. U sub t is minus p sub x. So I get rid of the t derivative by p sub x. Right? With a minus sign. So now I see to leading sigma 1 becomes an x derivative of p. Got it? So we get a term minus 4/3 epsilon squared p sub x. And it's missing, should be one more x. Typo by Sung-Yil Ha. Okay. Two derivatives. Okay, now you can continue the procedure. You see how it goes. It goes x with a u, xx with a p, 3 x's with a u, 4 x's with a p, etc. Back and forth, and the coefficients you have to keep track of. Okay. And the goal is add all those terms up. Okay. Sounds impossible. Even at this simple level, okay, not so simple. Okay. Everybody with me so far? Okay, I'm going very slowly because it's, okay. So, just for fun, before I add them up, let's do the truncation. If I truncate it at order epsilon, this is exactly missing something. If I If I truncate it at order 0, I'd get Euler order. But this is going this way. Okay, so it's the one above. So this one is truncation at Navier-Stokes order epsilon. Okay, and we look for solutions, checking stability. Look for solutions e to the I omega, e to the omega t, e to the I kx. It's just checking stability. If you want to think about it, it's taking Fourier transform and checking stability of the ODEs in the Fourier transform variables. Okay, in mechanics that's called, in physics it's called finding the dispersion relation. Okay, so Navier-Stokes order gives us this good term, k squared, and then this complex part. Okay, but actually it just says when k squared is 4k squared is minus 15, if there's no typos, then you have two negative real roots, and then when it becomes greater than 4k squared minus 15, two complex roots, but in the roots are in the left half plane. The real parts are in the left half plane, and we have stability. We go up Burnett order, okay? Same idea. Here we get imaginary part, but the real part is in the left half plane, so we still have stability. Let's go to super Burnett order, and now we see trouble coming in. We have this imaginary part, but you see when k squared is bigger than 3, the high frequency data, then this guy, k squared is bigger than 3, so this, okay, should say, why does he have should be a plus, again a typo by some here. Okay. So when k squared is bigger than 3, it becomes positive, and the roots move to the right half plane, and we have instability, okay, which is the Mobilev type instability. So what does it tell us? Even in this simple model of the grad with 10 moments, okay, and we do the Chapman-Enskog expansion, truncation after, in this case, epsilon, at order epsilon cubed, will lead to instability, as it must. It will always lead to instability at some level. It's not a, as I say it over and over again, the reason of the instability is not a physical reason. It's mathematics. It's just representative of alternating signs in power series expansions, with the power series of expansions that converge. Okay, let's continue. So as I said, the goal of the Chapman-Enskog expansion for Gorban and Karlin, their goal was not to truncate. That's a mistake. The goal is to add them all up. So let's just write down Chapman-Enskog, the first couple of terms. Remember, it went, if I'm not mistaken, 4/3, and then it was epsilon ux plus epsilon squared pxx, and then this epsilon. It goes, alternates u, pressure, velocity, pressure, velocity, pressure. So think about it. We had the PDEs. I don't want to go back. Okay? We had PDE that said something like u sub t, and with p sub x, p sub t with u sub x plus stuff, and that. Okay. And then we had a sigma. Okay. Take Fourier transform. So if we take Fourier transform, then that changes to just time derivative of Fourier transform, and this, depending on your definition of Fourier transform, becomes ik. So solve the PDEs by using Fourier transform technique. So take Fourier transform of the PDEs, which means that into the equation will not go the sigma, but the Fourier transform of sigma. So if I want to solve the PDEs using Fourier transform, what I need to do is take the Fourier transform of this guy. So let's do it. So take the Fourier transform, we get minus 4/3 epsilon ik u hat. I think I use minus for the Fourier transform, and then it would be epsilon squared ik squared p hat, etc. So we get a power series expansion in the k's. So we've changed the problem of adding the Fourier transform, adding up the Chapman-Enskog expansion, to a doable math problem. Because now everything is a classical classical power series in the k's. Okay, and if you want to see the form, here it is. It goes powers of, in fact, k squared times k. So this gives all the u's. Let's see, the u's had just odd, right? It was k and then k cubed. And the p's had just even. So the u's have the odd k's, and the p's have the even case, and then these coefficients, which I don't know. Okay, I know the first couple, 4/3. The first one for the A is 4/3, and the first, so A0 is 4/3, B0 is 4/3. Those two I know. The rest, okay, too much work. Okay. Well, we can rewrite this one. Okay, if you view all this, this is all these guys, this big sum multiplying the Fourier transform view. So call this big sum. Okay, has a coefficient ik. So it's this sum here, the ANs. Call that capital A. And this doesn't mean multiplication. It means capital A is a function of k squared. And do the same thing with the p part. So the p comes outside, the k squared comes outside, and this sum of the bn minus k squared, we call that a function of b of k squared. So here it is, the definitions. Okay. So everything comes down to adding up this power series. Okay. Now if you're with me, you're probably thinking to yourself, oh, he's got to use some of those tests from first year calculus to prove the power series converges. And that's good intuition, but not true. No, I will not do that. I will give you an exact formula for the sum. Not my idea, it was Gorban and Karlin. You can write down a closed form solution. Amazing, but true. So let's continue. Okay. The good fortune in this case, now this is a bit of a computation, so I won't bore you with it. It's in the papers of Gorban and Karlin. It's also in my research papers. I redid it. Okay. You can add up, find the exact formula for A and B. There's two terms, A and B, but they're not independent. The capital A and the capital B are related to each other. That is, if you divide, and they're related to each other by the following formula. The capital A is equal to B divided by 1 minus k squared B. This is major philosophical implication in my opinion. Okay, what does it say? Remember, the A came from the U stuff, and the B came from the P stuff. Now what does it tell us? You can't have one without the other because one is related to the other. You can't have the B stuff, which comes from the P's, equal to 0, and just keep the A stuff, which is exactly what the engineers do in the books. They say, oh, we don't like, we'll stop at order here and do Navier-Stokes Fourier and throw away all these terms. But it makes no sense because you can't set one equal to the other. So there's two things. You could say, okay, if you're going to keep this one and throw away these, okay, that means you're assuming that all these derivatives are small and epsilon square guy and epsilon cube guy are small, which is okay for smooth solutions. Okay, that is these derivatives. But remember, just as I told you, if we were looking for traveling waves, for every x derivative, the epsilon's got to cancel out. For every xx derivative, the epsilon square's got to cancel out. For every x cube, three derivatives, the epsilon cube will cancel out. Okay. All terms, when you're looking at traveling waves, are the same size. So inside the shock layer, you can't just keep, there's no way. Okay. You don't have the smoothness, and you can't throw away the B without throwing away the A. Okay. So then the question is, if A depends on B, what are they? Tell me what A is, or tell me what B is. Well, let's just define another version of B. If I know B, I know A. Hence, let's multiply B by k squared. So if I know, I call that C. So if I know C, I know B. If I know B, I know A. And if I know A and B, I know everything. Okay. So what's C? Well, the thing is, because you have a recursion formula for these coefficients, and the thing is rigged up, I'll say it in words, I don't show it here, that this recursion formula is a convolution, a discrete convolution. And what's good about convolutions, Fourier transform or Laplace transform, is the transform of the convolution is the product of the transforms. The same thing. You can do a transform in K-space and then get a closed form expansion, and that's how it works. Okay, so what's the point? Is that the C solves a cubic equation, which I call the fundamental cubic. So, if we solve the cubic, we know C. If we know C, we know B. If we know B, I know A. I know everything. And this is a nice cubic guy. Okay, so this is a good excuse to look at Cardano's formula if you haven't used Cardano's formula lately. I use Cardano's formula. I don't know how Gorban and Karlin did it, but I've solved for the solution explicitly. Okay, now it has one real root and two complex roots. Okay, I don't care about the complex roots because I'm looking for the coefficients here, which should have been, okay, only the real root, okay, to give me the A and B I want to be real. That's the only one that makes physical sense. Okay, and the real root is the one of interest, and it's negative for K squared. So the graph, I think I have it on the next page. So in fact, we can make a graph of C. So you have C, okay, on the axis, and K squared like this. So C and minus 4/3, or 4/5, sorry. So it's easy to make a graph of C. So we know C, can make a picture, and the graph looks like that. So it's negative and asymptotes to minus 4/5. So now I know C. I just drew a graph of C. I know C, I know A. If I know C, I know B. If I know B, I know A. I know AB. I know everything. I've summed the Chapman-Enskog expansion. Fantastic. So let's go back to the PDEs, but in Fourier space. So I take Fourier transform of the PDEs. And here it is. So there are the PDEs, and there's the A and the B entering through the sigma. Okay? And remember, I know A and B. Okay. Let's check stability of the equilibrium state. Remember, the stability was good up until, what is it, Super-Binet order, and then things got bad. Okay? But this is the exact sum. If it's the exact sum, it should be representing the Boltzmann equation. Exactly. Okay? At least it should be the exact representation of this 10 moments. Well, if it's to make physical sense, then the rest state should be stable. The air in the room, if we to give it a small perturbation, better return to its rest state. Okay. So let's do it. So we plug in, just like you would in an elementary course, you look for solutions e to the omega t times p and e to the omega t times capital U. So just, okay, like any course in linear ODE, you plug in, you get this matrix, okay, you cancel the e to the omega t stuff, hitting pu equals 0, and remember, so this just says the omega, of course, is just appearing as an eigenvalue. It's an eigenvalue problem. So the question is, are the eigenvalues, the omegas, in the left half plane or in the right half plane? So we do that. Okay, and I'll do the computation for you. So we have to use the quadratic formula. As I said, it's elementary mathematics. So we use the quadratic formula. That takes a little manipulation. Okay, so do the quadratic formula, solve for omega using the quadratic formula. They have to use the definition of C. Remember, C solved the cubic. So we can solve the quadratic formula, and here's the expression. Okay, now because of the definition of C, this guy is positive. So I'm taking the square root of a positive number, which is good. It's multiplied by I, so this is the imaginary part. And how about this guy? Well, C is negative, so the numerator is negative, but C is, again, let's see, C is going to minus 4/5. Again, Ha may have left out a sign. I never see, so this is, I think he left out, again, a typo, so it should be minus. So this part is to be negative, so it should have been minus, right? Because C is negative, and negative minus negative is negative. Negative over negative is positive, so you left out a minus. That's what happens when you let somebody else do your slides. But I don't know how to type. Okay, so the omegas are all in the left half plane. So let's continue. And here's a picture. The picture is correct. So I graphed the spectrum. Okay, so here's the omegas coming from the exact sum of the Chapman-Enskog expansion. And you see the good news and the bad news. Okay. The good news is they're in their left half plane, which indicates stability. So what could be bad? But the bad news is, well, think about, what does the spectrum, say, from the Laplacian look like? Okay, it goes over like this. Goes out to, it's the theory, elliptic theory, okay, or Sturm-Liouville theory, okay. And they all have to go out like this. Sturm-Liouville, of course, they just go like this, okay. But what's happening here? It has an imaginary part. The Laplacian would all be on the negative axis. Here, it has an imaginary part, and it's asymptoting this way. So what does that tell us? That means, okay, it's damped oscillations, but the oscillations are getting bigger, while the damping is not getting any bigger. Okay. So the exact sum is introducing something with dissipation, but it's having problems dissipating. Let's continue. Okay. Then I mentioned one aspect not addressed by Gorban and Karlin is an energy or entropy inequality. Surprisingly, they didn't do it. So it's nothing more. You multiply one equation by P, the other equation by U, and you add them together. It's like getting a Lyapunov function. So we do that. And we get ddt, okay, of this guy's. This is just, okay, magnitude of the complex numbers P hat and U hat, complex information. Here's the ddx term, but in complex form. Okay, and then this the leftover stuff. Okay, let's use the first term, the P sub t equals U sub, this should have been U. Okay, P sub t equals U sub ik U sub x. Plug that in to get rid of the, rewrite the equation. And here's the energy equation again. So it's d dt of this guy equals a ddx type term. I'll change it back to physical space in a minute. And then a damping term. Okay. Remember, C was negative, which gives A negative from the formula. Okay, I'll write it again. I want to get to the important stuff. So here's the equation in, let's integrate over Fourier space, k minus infinity to plus infinity. Okay, so we integrate over Fourier space, so we get something like the L2 norm of the P and the U, which is good. We get this, this term, which of course is a ddx of UP, so this would integrate out. Okay. Here's a ddt of the stuff coming from the B, which is nu. And here's the damping term, which comes from would be the viscosity, the viscous-like behavior. Okay, I even write it out again. I use, for those who've taken elementary, whatever, first year graduate course, Parseval. So L2 inner products in Fourier space are equal to L2 inner products in real space. That's Parseval. So I can change it into, it's not a mistake, this one is not a typo. Okay, I switched K integration to X integration. So this really looks like the L2 norm of UP. Okay. The ddx term integrated out, and now we have a ddt term of this extra guy from the B. Remember, B has the P guy, P squared, the term there. I should use the, okay. So this would be the normal energy. What do we have here? We have a new addition to the energy coming from the P. And here's the normal viscous type term. So I make it in red here. Okay, this term, okay, is a new contribution to the energy, not in Navier-Stokes Fourier theory. Okay. So it's a non-local version of what would be called, I call, and Korteweg would call, back at the beginning of the 20th century, capillarity. This term on the right-hand side, okay, so this is a non-local version of capillarity, which is not a Navier-Stokes Fourier, and this is a non-local version of viscous dissipation, which is a Navier-Stokes Fourier. That is, in Navier-Stokes Fourier, we would have epsilon uxx. Let's just do the simple example that I did before. We'd multiply both sides by u, and you get epsilon uxx. We'd integrate by parts and we get u minus x squared. And that's that term. Okay. But when you do the classical Burger's equation, this term would not be there. Okay, let's continue. So let's write the energy identity. There it is again. Okay, since A and B are negative, this makes sense. Here there's no typos, fortunately. B is negative, so this is minus times the negative is positive. So this is ddt of the L2 norm plus ddt of a new term, capillarity energy, equals viscous dissipation. A is negative since C was negative. So I wrote it down. It says the physical principle is ddt of the mechanical energy here plus ddt of the capillarity energy there equals the viscous dissipation. This is exactly as given by Korteweg's theory of capillarity, which he wrote down roughly in 1904, plus or minus something. Okay. So what do we see? We see the exact summation of the Chapman-Enskog expansion has yielded a non-local version of Korteweg's theory from the beginning of the 20th century and not Navier-Stokes theory. So the bottom line, which I'll continue, okay, is if you want to know how to understand what's going on in a shock wave and you want to use one of these theories, okay, the justification given for Navier-Stokes Fourier theory is not valid, makes no sense. The correct justification based on Boltzmann is Korteweg's theory, which he wrote down more than 100 years ago. So, is the theory really non-local or not? Okay. And the answer is, okay, my opinion is, the theory is non-local because of the truncations that we did moments, not truncations in epsilon, truncations in moments. If we had carried out more moments, my belief based on the work of Ruggeri and Boileau, French mathematician, Italian mathematician, is you use more moments, it'll begin to look more and more like PDEs. Okay, so, and that somebody should do that. I give some hint here. But let's continue, because I don't want to run out of time. Okay. Hence, we could expect that if we let the number of moments increase, we would get a linearization of Korteweg's theory. So I haven't told you what Korteweg's theory is, so let me remind you of Korteweg's theory. Well, it's a little messy. So what it is, it's an improvement, or it goes beyond Navier-Stokes theory, and it adds more terms into the stress tensor. Let's write down, so here's the balance of energy equation in Korteweg's theory. Remember, that was just the one I had done before within the simple model. So what do we have? We'd have the U squared term. We'd have something like the L2 norm of the density squared. And what do we see in Korteweg's theory? We have a gradient of rho squared, a new contribution to the energy. That's the capillarity contribution to the energy. And on the right-hand side, viscous dissipation, as is classical. Okay, let's do the summary, and then let's think about it. Okay, so the summary and okay, so I've shown you that Gorban and Karlin's Chapman theory leads to something like Korteweg theory. Okay, in fact, a non-local version of Korteweg theory. But the Korteweg theory, let's go back, has this additional term. If I had rescaled and put in the Knudsen number, I'd get, for each I, I'd get an epsilon. So I get a term, epsilon squared, gradient of rho squared. To produce, okay, the Euler equations of continuum mechanics, that term would have to go to 0. So we'd have to have epsilon, a little PDE, not much. So we'd have to have epsilon squared, gradient rho squared. There's a rho, but that's irrelevant. That integral, integrated over the domain, would have to go to 0 as epsilon goes to 0. Well, for smooth solutions, okay, probably the gradient of rho is bounded. You square it, it's bounded. You multiply by epsilon squared, goes to 0. But for non-smooth solution, okay, gradient of rho is unbounded. In fact, what do we know? From the original energy estimate itself, we know that this guy is less than 0 because its d dt of this stuff is decreasing, so this guy must be bounded. So all we know is, in terms of functional analysis, we have a sequence f sub epsilon in L2, which is bounded. Let epsilon go to 0. Does it converge? Maybe yes, maybe no. All we know is it has weak convergence, but weak convergence doesn't imply strong convergence. Okay. So we do not know that this term will go to 0. For smooth solutions, of course. For weak solutions, not. So, and I'll tell the story. I was riding with Taiping Lu in Yongjung's automobile, I think, last spring. And Taiping said to me, "Oh, come on. Look, I proved that for the Boltzmann equation," he said, this is one of his really great theorems. It's true. "I proved that this is a solution to the Boltzmann equation that makes the shock transition, and rho, this is x, that's rho, and rho goes from -1 to minus rho to plus. It's positive, and it makes a smooth transition." Okay, that's the shock wave for Boltzmann. The smooth, okay, that's the solution to Boltzmann, which should be capturing the shock in the layer. And I said, Taiping, let's think about this for 2 seconds. Okay. In the limit of what would Taiping's solution look like? Well, of course, it's going to look like a Heaviside function. Okay? That would be the epsilon limit, because rho is a function of x minus ct. It would look like a Heaviside function. The two pieces would contract, it would look like a Heaviside function. If you differentiate a Heaviside function, you get a delta function. What's this say? You're taking a delta function, that's perfectly okay, and squaring it. Not allowed in mathematics in my life. Okay, makes no sense. So, okay, in the shock wave, this term, which is being produced by Chapman-Enskog, is not producing a delta function. That would be okay. It is producing a delta function squared, which is not okay. You cannot make mathematical sense of it. Okay, let's continue. I have still a few minutes. So, from the point of view of quarter-vector theory, the Chapman-Enskog and hence Boltzmann is not looking good as epsilon goes to 0. You're producing an additional term. Another way to say it is the Navier-Stokes Fourier theory. Outside of the shock wave, Boltzmann is giving it. Hilbert was right. But inside the shock wave, Hilbert was wrong. Okay, this term should go to 0 in the sense of distributions, but I just tried to convince you that it looks like a delta function squared, not looking very good to go to 0 in the sense of distribution. Okay, now there's an analogy that is very nice. It's not derivable, okay, but just as Burgers is a good example. The analogy here to KdV is very nice. So remember we had Burgers, and now let's put in next higher derivative. So this is trying to capture the capillarity story. Okay. So what's going on? Okay. If, as I said, if I put my hand over, putting in 3 derivatives on the right-hand side, if I put my hand over that term, letting epsilon go to 0, everybody's happy. You can prove it, I don't know, 2, 3 different ways. On the other hand, if you put your hand over that way and try to let epsilon go to 0, not true. Only converges to the shock wave, okay, converges to the solution before the shock wave forms. After the shock wave form, it's not just you can't prove it, it's definitely not true. You can solve this equation explicitly and see what's going on. And you do not converge to that one. And that's 3 papers of Lax and Livermore back in the, I guess, early 80s. Okay, so, but then the question is, my claim is that Boltzmann is producing something like this, and they're both there. So it's a competition between the good guy and the bad guy. And who wins? Well, it's easy to see. The first paper on this, and I think I have it. So this is called KdV Burgers. And the question is, it all depends on the size of the capital K, which is our capillarity-like coefficient. I use K because it's first letter of Korteweg. Notice Korteweg's name appears twice here for 2 different theories. One is the Korteweg-de Vries equation, and one is this Korteweg theory of capillarity. Needless to say, okay, he was thinking about both. It makes sense, the same guy. Korteweg was a smart guy. And he saw this role of the higher order term. Okay, so the limiting procedure, which one wins, the first paper, as I say here, was done by Maria Schoenbeck in the 80s. And the answer is clear. It's easy to see. Of course, if K is very big, that's bad. If K is very small, that's good. What's the cutoff? And there's 2 ways to see it. One is to look for the traveling wave solutions and see if you can make the transition. Okay, for this one, you can't always get traveling wave solutions. You can get a soliton, but general traveling wave solutions, no. And my guess is, going back to Taiping's remark, Taiping said, oh, I got the traveling wave. And I thought about it. I said, now Taiping isn't here, and I won't see him. Okay, and I'm thinking, what did Taiping find? He found the soliton. the traveling wave for the KdV equation. Okay. But he did not find the connecting wave. That's my opinion. Okay. So how do you find? So one way is to look for traveling waves, and you see how big K has to be. Another way is just to do linearization and check stability. Okay. Okay. But I have a better way, I think, which can go back to the original issue of Boltzmann. So I have 5 minutes and I'll finish. It's less. Okay. That is, if you remember, well, in conservation laws, I said one way to check, going back historically, whether we have a good shock or a not good shock, etc., was to put in the epsilon uxx here. That is, this should look like Laplacian on the right-hand side. Okay. What if people then continued? They've done it for systems. So now, U is a vector, okay? And the question is asked, for a system of equations, can you pass to solve the conservation law as a limit as epsilon goes to 0? Hard problem. And the answer was, in fact, yes, okay, under certain restrictions on the data. And that was done by Stefano Bianchini, who was just here at NIMS, Bianchini, okay, last year. Actually, this year, 2012, in the spring. So Stefano was here. Unfortunately, didn't lecture on that. But it was a big result. He proved that viscosity works for systems in one space dimension. So what's the point? Okay, that is, if this Boltzmann, it's all a linear viscosity here. So it's not a nonlinear issue. So if Boltzmann would give us linear viscosity on the right-hand side as a system, we think we'd stand a chance based on Stefano's results. So let's see what this Chapman-Enskog expansion that I've summed gives us. So if everybody with me, I hope. So I'm going back. I've summed Chapman-Enskog. I got the capital A, the capital B. But now let's write it as a second-order equation. Okay, you eliminate one. It's two first-order equations. Write it as one second-order equation. Okay. Factor it. Okay, I like to do this. I've been doing it in a couple of old papers. Okay, so if we factor it, then I've rewritten this equation now as a second-order equation, but in factored form. But I have to tell you what mu1 and mu2 are. Well, it's not hard. You multiply it out and identify what mu1 and mu2 are. Okay, give me one more slide and I'm finished. Okay. So it's easy to find mu1 and mu2. Okay. So now the equations, okay, look like, okay, d dt, this is a d dx in physical space, so this is the conservation law. And this is the viscous terms. So if mu1 and mu2 are real, okay, which would be the Fourier transform here, then I've reproduced viscosity. And it stands based on Stefano's result that we should be able to reproduce solve the Euler equations. There's no limit. So what are mu1 and mu2? Well, it's algebra. In fact, I should. Okay. So there's in physical space what the equations would look like. It looks like conservation laws and then some stuff. But what do mu1 and mu2 look like? Okay, here's the formulas. So mu1 and mu2, this is no typos, I think. Okay, it has this. Okay, this one is correct, right? C is negative, so this is negative, positive, positive. So he has a. Is it plus or minus? So how did he write it? Anyways. So it should be they should have in the left half plane. Again, I don't trust the typos. Okay, but it has this complex part. So it's not reproducing viscosity, it's producing an oscillatory contribution. So again, it's that what we would do for conservation laws is this, and we know it works. From Boltzmann we don't get this. We get a complex contribution. We get this imaginary part. So that there are oscillations going on in this limiting procedure. Okay. So the capillarity effect is strong enough that we have these oscillating guys. Doesn't look good for Stefano result. Okay. So what's the final thing? I have going over 1 minute, but that's okay, I hope. So Hilbert's hope may have been justified in 1900 because Hilbert, he wasn't, weak solutions hadn't been invented yet. Okay. Okay. So Boltzmann was a good guess, but what mathematicians have tried to do is push the theory down into the shock layer and capture the weak solutions. And my view based on these elementary arguments is just not true. Okay, so I suggest many things if you want to carry it out, but I don't think Hilbert was right. Okay. That's it. Bye-bye. See you next week.